This on, right.
Hi, welcome back. This is section 1.8 for linear algebra. So I was able to cover the last video a lot faster and quite concisely than what I'm used to. So that's a good sign. Hopefully that trend will continue. Yeah, so let's just blitz through this this section and then call it a day. This unit has been a little bit confusing, to me at least, because they introduced the idea of transformation, which isn't anything new, but the way they explained it was, I don't think it was their finest moment for the profs. Don't mean to be rude, that's just my impression. So hopefully how I understood it through pain and suffering will make more sense, or, you know, we'll see how that goes. Anyways, so first question, and the question is basically asking, find the domain and domain of the transformation T ax equals to ax. Technically, x should be x vector, and then T ax, I think, transformation due to a based on x. How do I say that? Because if it's like f of x, right? A transformation of a based on x. So it's like f of x. So transformation of x based on a. I'm gonna have to figure out how to say this properly. But nonetheless, okay. So the point is you're trying to find the domain and codomain, which is pretty easy. But I want to explain what is happening from the scratch, so that when we look at other questions, you don't get us fumbled, because that's what happened to me. Okay. So we'll start over here. So it looks a little bit convoluted, but the TAX literally just means, okay, we're gonna use this target matrix and then use that to transform whatever this x vector is into our resultant vector, which is WE, right? They don't mention that in the question, but you know that W vector is essentially TAX, right? I mean, equation-wise, because this thing are equal, right? So think of it this way. A is the matrix that we're used to, right? Like if it's 3 by 3, let's say 1, 2, 5, and then 3, 5, 6, and so forth, right? And x is a vector, so that just says x1, x2, x3, that sort of thing, right? And basically, W vector is what they equal to. Remember the constant column? That's always at the last, right? So visualize that way, and as we go through it, it will make more sense. Okay, so yeah. So my strategy is that I look at the a and the vector x, right? So basically this a is the standard. This is a matrix, and then vector x is what is being transformed. What is the starting point for this transformation, right? And then W vector is the net change of the transformation. So think of it this way. So let's say vector x is the cocoa powder or whatever, right? And then W vector is the chocolate bar. And the A, the matrix, is the machine that gets the input of a cocoa powder and then transform it into chocolate bar. So most of the questions that for domain and codomain, that's like asking, well, what was your starting input, right? So that's obviously the cocoa powder. It's a horrible analogy, I know, but yeah. So that's what domain is. Your input, your starting point, right? And then and the W vector, which is your output, right? That is your chocolate bar, right? So think of it that way. Hopefully that sort of makes sense. But let's get into the math, right? So all we know is that A has a size of 3 by 2. Now, A and the x vector, they're going to multiply together, right? And as we remember from the multiplication rule, from the multiplication matrix sections long ago, right? So if A is 3 by 2, I'm not sure what these two vector is, right? But this has got to be 2 by something, right? If it's not 2 by something, then these two cannot cancel out, which means we can't do multiplication. Right? So that's not a possible scenario for transformation. In order to transform something, we need to be able to multiply it, right? I mean, the what do you call it? That's a shell case stamper. We'll have to. Okay, no, that's actually a horrible example. Okay, let's go back to cocoa. I was keep thinking of AK-47 for some reason, but nonetheless, weird attention span. But yeah, so in order for cocoa powder to turn into the chocolate bar, you have to have a machine that's compatible. If the machine and the cocoa powder are not compatible, then you're going to have a crisis, right? Because your machine's not capable of using your input to produce an output, right? So think of it that way. So in order for 3 by 2 to multiply to x vector, the x vector has to start with 2. Now, where did 1 come from, right? Because remember, x is a vector, right? Remember, we covered a lot of this in the earlier unit, right? Vector x is like x1, x2, x3, and so on, and so on, and so on, right? So because we're listing all the unknowns, or in this case, x1, x2, and so forth, right? So because of that, they all have to be one column. You can't have multiple columns, right? Because we're just trying to describe the vector direction. You can't have, if you have x1, x2, x3, there's direction x1, x2, x3. You can't have a direction within a direction. Actually, you can, but we're not covering it at this stage, right? So just go with it for now, right? So because of that, your final vector dimension must be, because you're multiplying 3 by 2 and 2 by 1, it must be 3 by 1. Now, let's try to make sense of this visually in a way that made sense to us in earlier sections, right? So A is like a standard matrix, right? It's 3 by 2, so 3 rows and 2 columns. So we're familiar with that, right? So as I've said, x vector, that's going to be x1, x2. The reason why there's only one x2 or two x variables here, unknowns here, is because look at the column. It's 3 by 2, right? So first column is going to be x1, and second column is going to be x2, right? That's why there's x1 and x2. There can't be x3 because according to 3 by 2 matrix here, if there's x3, then I gotta have 3 by 3 dimension, which is not the case, clearly. So that's why we stop at x1 and x2. Doesn't mean it's always going to be x1 and x2. Depending on what matrix A you're working with, you may have 3 by 1, or 4 by 1, or 7 by 1, or 1,000,000 by 1. Sky's the limit. It all depends on what the A dimension is, right? So if I times this together, you're going to have to see W1, W2, W3, because it's 3 by 1, right? So how did this happen, right? Let's look at this one. So basically what happens is you're going to times this with this, right? Standard matrix, right? So that's going to be whatever number x1, whatever number x2 will give me w1, right? And then same and repeat goes, right? So really, this fancy thing is really just this, the same question that we've been solving for ages, right? Look at it. This is just typical linear equations, right? Some number x1, some number x2 gives you w1, right? So that really is like 3 by 3 matrix, and then we have to find the unknown x's, right? That is the kind of questions we've been doing for a long time. So essentially, that's sort of what we're doing, right? We're just asking the question with a little bit of a different angle, and that's going to help us with other sections later on in section 2, which we haven't quite covered yet, and you don't have to worry about the upcoming quiz, but we will eventually, right? So anywho, yeah, so hopefully that makes a little more sense visually, right? So yeah, so okay, so anyways, back to the question. So what is a domain and what is a codomain? Domain is simply the input, right? As we've said, right? So input is what? 2 by 1, right? So because it's 2 by 1, row determines the dimension, okay? Row determines the dimension. So because of that, how many rows are there for the x vector? There's 2, right? 2 by 1, right? So because of that, we say this x vector is r, well, it's not r, it's ir squared. That's how the profs write it. On your solution manual, it just simply says r. I don't think they're going to give us wrong answers for that kind of trivial technicality, but I think it's ir. So how you write that is just, I. They write it in a funny way, and then draw like a small I, right? A little bit smaller, and then put so that it looks like almost like IR, right? I think that's what it means, but adopt appropriately. Worst case scenario, just write R. Yeah? So, anyways, that's what it is. And as we talked about, W, which happens to be this third column, is 3 by 1, as we said, right? So that's going to be 3 dimension, right? R cubed, right? So the starting point, X vector, will be the domain, and the codomain, right, is according to what Maria said. For now, think of it as like a range, like a Y that from calculus, right? Like y equals x, like f of x equals to x, or something like that, right? So because of that, so treat codomain as a y, right? A domain is the x, right? And the changes that are happening to x that will eventually give you a y net, a result, which happens to be the codomain, right? So, yeah, so essentially that. If you remember f of x equals x format from calculus, right? So depending on how we change the x, it will result in a different y, right? So x equals to y is going to be different from x cubed to the power x cubed equals to y, right? So depending on what actually that's a good example. So if it's x cubed equals y, and pretend that was a linear algebra equation, so that will be so starting point is x cubed, which is 3 dimension, right? So r cubed, and then transform into y, which is 1 dimension, so that will be r1. So there you go. That's a good example. Yeah, I'm not sure if that's the most appropriate example because that's beyond my expertise, right? But nonetheless, that's a good analogy. So think of it that way, right? So to summarize the big picture, so what that A matrix is, right? That A matrix transforms the input or an X vector into Y or W vector, right? And then it's gonna change its dimension, and that's the whole point. That's the big grand picture of this whole section, which doesn't seem that way, but ultimately that's all there is, right? Exactly. So for this case, we already talked about domain, which is R2, and codomain is R3, right? Okay. Moving on to B, so this time A is 2 by 3, right? So again, if it's 2 by 3, then the X component better start with 3, right? Otherwise, we can't even multiply, right? Now, what could the other one be? Well, again, it's X vector, right? So it's describing all the dimensions, right? So it better be 1. It should be simple, like x1, x2, x3, right? There is no x1, 2, x1, 3, and so forth. We could do that, but not for this section, right? So we're keeping the vector relatively simple, right? So anyways, so because of that, as you can see right here, so my A was 2 by 3, X is 3 by 1, and if you times it together, your overall net vector, I apologize for making a lot of trivial mistakes, but that W is going to have a dimension of 2 by 1, okay? So again, the question here, we're not trying to understand the whole thing. I explained it anyway for future reference, but this question specifically are just looking for domain and codomain, right? So for this one, domain will be the X vector, that's your input, which is 3 dimension, right? So that's going to be R3, and then my output, which is the codomain, is 2 by 1, so that's 2 dimension, right? So that's R2. That's all there is. Nothing all that difficult. So I wouldn't as soon as you appreciate that, I wouldn't really bother like practicing bunch of questions for at least not until we get to maybe 7. But anyways, that's that, and I gave you I tried question 2C, just so that you guys know what you guys are doing, right? So. Oh, another thing is that just when A transforms, right, or whatever matrix transforms, right, it doesn't always transform from higher matrix to lower matrix. I mean, that's a trend. But transform just means changing from one dimension to another dimension. And technically speaking, if the original matrix is 0, we'll figure that out later, right? Then there is no transformation, right? There's a transformation by 0. I don't know some people might say that's technically not transformation, but technically, I mean, even if you don't transformation by a factor of 1 is still a transformation. Nothing has changed, but you transformed it, right? By timesing it 1, right? So it just means transform, right? So you could go from R2 to R5, or it could be R10 to R1, or maybe it will stay the same. It will be R3 to R3, right? Doesn't really matter, right? All we're trying to do, all we know is that it will transform. Not the way we think it may be, but anyways, I think I've talked enough about that, right? So anyways, to see, so if A is 4 by 4, obviously the x vector or the domain has to start with 4, otherwise nothing will happen. So that's 1. So the domain is going to be 4 by 1 or R4. Now, interesting here though, the dimension doesn't change, right? Because the 4 and 4 cancel out, you're going to have a final, you're going to have a codomain, which also happens to be 4 by 1. So that's also R4, right? So domain and codomain for this case will be the same, which is R4, right? So that's all there is. I think this is going to be concise. Oh no, I already wasted a lot of time. But anyways, so 3A, a similar idea, right? So basically this time, rather than giving you the dimension, they're actually giving you the matrix. So look at it. So this is a linear equation they gave you. I already changed into to matrix format. So A is going to be just 4, 5, 1, negative 8. Just how we always find the standard matrix, right? And the x vector is going to be x1 and x2 because it's 2 by 2. There's x1 for column 1, x2 for column 2. There is no x3, x4 for this case, right? And that will give you some constant value. It's going to be w1 or w2, right? So again, so if I put it in this way, this is A is 2 by 2, x vector is 2 by 1, and w is 2 by 1, right? So again, domain is R2, and the codomain is also R2, right? Because they're both 2 by 1 and 2 by 1. So in this case, there's no dimensional change. So domain and codomain are the same. They are both equal to R2. Let's look at 4A. Again, very similar idea, right? So they give you these equations and then, so again, follow the pattern. I think you guys are smart enough to see the pattern. So I'll just let you read it. And 5A, again, same idea, right? So I don't want to get too repetitive. Actually, I am very repetitive. But you see the pattern here, right? So basically, I want you to understand that. Things where it gets a little bit, it's the thing that goes a little sideways is 7 and 8. So again, nothing too difficult. It's just, a little different way of showing it, right? So basically the question goes like this. So 7b, for example, t, x1, x2, x3 equals to whatever, right? So it looks complicated, but think of it this way. This is your starting vector, right? So essentially this is x vector, right? And whatever that produces is going to be your constant column, right? Which is your w vector, right? Vector w, or I don't know what you say first, vector w or w vector? X vector. X vector sounds cooler than vector x. No, they both sound cool. Anyways, but doesn't matter. We're not being tested orally, right? So, so again, how many dimensions are there? So x1, x2, x3. So there must be 3 columns, right? 3 columns. And so we say, okay. So basically we're going to have some kind of matrix that's 3 by 3. Now we can safely assume that, right? Because of that, domain will be R3. Now look at the output, which is codomain, right? So this is where you have to be careful. I know there's a lot of fancy things going on, but this merely shows you what has happened. You put in the x1, and with these changes, now you're going to have a new output, right? So this is going to be, this whole expression here, it's going to be w1. So that's going to be w1, and that's going to be w2. So I apologize. This is not going to be 3 by 3. We can get a hint, right? Because this is 3 by 1, and this is 2 by 1, right? So 3 by 1 equals 2 by 1. So what is my original matrix going to be? Well, obviously it's going to be 3 here, right? So that they cancel out. This is 2 and 1, so there must be 2 in front. So I apologize. This is not 3 by 3. It will be 2 by 3, right? But nonetheless, we get the idea, right? So this is that, right? This x vector is that, and w vector is going to be that, right? So after we realize this, it's the same thing as what we've been doing, right? So let's see here. So that's going to be three-dimensional. This is going to be 2, right? Because there's 1. Focus on the comma, right? I made a lot of mistakes because I didn't see the comma properly. So I got the wrong dimensions and I got it wrong, and it's unfortunate, right? So make sure you pay attention to the comma and figure out how many how many dimensions are there for W vector, right? So that's 2. So yeah, there you go. 8A, same idea, right? 1, 2, 3, 4. There's 1, 2. So starting domain is r to the power 4. Codomain is r to the power 2. Yeah. It's not rocket science. Okay, so okay, moving on to question 9. Again, it's the same idea, right? But so they just put it in a little bit different format. So this is just like f of x equals to y, right? So transformation using this input x1, x2, which happens to be an x vector, and remember x vector was the domain, right? Your input, right? That will give you this resultant vector, which is w vector, right? So that's gonna be 1, 2, 3. Don't get confused by this x1 minus x2 thing. It doesn't really matter. It just shows you what transformation has happened. The important thing is there are still 3 dimensions, right? 1, 2, 3. So that's going to be 3 by 2, and this is 2 by 1. So 3 by 1 and 2 by 1, right? So this is just so that I can convert this into a format that we're comfortable with. But ultimately, it's the same thing as we've been doing, right? So input domain is going to be R2, and the output domain is going to be R3, as shown here. And if there's ever a question about, well, tell me what kind of transformation it is, right? Then you could just say, well, input is x vector, and output is w vector, and so basically starts from R2 to R3. So from 2 dimension to 3 dimension. That's all there is, right? Question 10, again, same idea. So I'd rather not get too repetitive about this, but it's the same idea, so just follow through. It should make total sense at this point. 13 is a little different, however, simply because basically we have a similar format like we are used to, right? But rather than trying to figure out what's the domain, codomain, or what kind of transformation is happening, it's asking what transformation actually takes place so that the input becomes the new output, right? So tell me what change is being made, right? Not just, oh, it's converting from 2 dimensions to 3 dimensions, like what happens to the first vector, right? A second vector, like what changes, right? So because of that, we need to find what AX is, right? And what we know X vector and W vector, right? So X vector is 2 by 1, X1 and X2. W is going to be 1, so remember, count the commas, right? Be careful. 1, 2, 3, 4. So there's going to be 4, R4, so that's going to have 4 rows and it's going to have 2 rows, right? Now, think of it this way. So I'm just putting this copy here, right? I wrote the dimension already, but let's assume we didn't know that, right? 2 by 1 and 4 by 1. These two we know for sure because those are given, right? Then in order for this to happen, you have to have 4 by 2. That way 2 and 2 cancel, so 4 by 1, and then you have 4 by 1, right? So this is how I like to see it, just to make things a little better, right? So think of it this way: A, I, X equals to W vector, right? So nothing different from what I've done. All I did was I did a matrix to it, which shouldn't make any difference because I is just essentially 1, right? Algebraically speaking, right? So if that's the case, I'm gonna have A, right? I don't know what the matrix is, but it's gonna be times of I, which is 1, 0, 0, 1. Why 1, 0, 0, 1? Because the vector we're using, right, is 2 by 1. It has to, right? Because this first row is x1, and this second column, first column is x1, second column is x2. There are no other columns, so this is the identity matrix we're using for sure, right? So that's gonna equal to W, which is gonna be x1, x2, like, just whatever is up there, right? So that's why, all we're saying is, okay, so this is this. I don't know what happened, but I don't know what happened with this A, but it gives you that, right? So we use X vector as their reference. right? So that's what we do. So if you look at it, the identity matrix here, that's row 1, that's row 2, right? So when we look at these, we're going to actually use that method, right? So look at it. It says x2, right? What is x2, right? That's gonna be the, see, first row is x1, right? Because there's x1 and there's x2, but x2 is 0. So we don't know, right? So we're gonna use the second row because that's where x2 is defined. So this is what I'm gonna use. So that's gonna go right here. That's x2, right? Negative x1, what is that? Right? So negative 1x is, x is defined here, right? So that's x1, but it says negative. So I just times this first row by negative 1, and you're going to have negative 1, 0. Third row, x1 plus 3x2. Well, x1 is 1, so it's right there. x2 is 3, right? So that means this 0, 1 times 3, and that will give you 3. So that's why you have 1, 3, right? 1x1 from x1 here, and then x3 because this row defines x2 and you times that by 3. Same thing applies. x1 minus x2. What is that, right? So that's the last one. So x1 is 1 right here, right? So we put 1 here. x2 is this guy, right? That's x2 is defined. But remember, it's minus x2, right? So that becomes negative. And that's really all there is, right? We'll do more of these examples as we go on, but nothing too complicated, right? Just make sure you're comfortable with this format, and then you should be okay for the test. All right, next one, 13C. So we're going to do a similar thing that we've done before, right? So this one's a little weird, though, in terms, at least aesthetically. It's the same idea. It's because, see, we're trying to find what A is. And that's going to be x1, x2, x3. Oh, yeah, by the way, before I go further. So this, well, I already sort of mentioned. So whatever you find here after you made these changes, this is going to be your A, right? So, and you can check this too, right? This times x1 and x2, this x vector, will give me this new vector, right? That's all there is. Yeah, so. Alright, so, yeah, moving on, 13C. So as I've been saying, aesthetically it looks weird because of this, W vector is all 0. What is going on, right? So, again, let's put it into a format that we are comfortable, right? So, x vector is 3 by 1. That's obvious because that's given to you. W vector, you have to be careful with this. I know they're all 0. But remember, there's a difference between vector 0 and just plain 0, right? We talked about that in 1.6. So if it has 5 zeros, like this fashion, then it's not just 0, it's vector 0, which means the dimension is 5 by 1. This is important, because if it was just 1 by 1, we can't do these multiplication. 3 by 1, what are you going to be able to time? Oh, yeah, never mind. Anyways. So that's the important part, right? So like we did before, use x vector as a reference. So I'm gonna use the identity matrix based on the x vector, right? So that's 3 by 1. So that's gonna be 1 0 0 0 1 0 0 0 1. We've seen this identity matrix before that has a dimension of 3 by 3, right? So now what I have to now do is I have to somehow use this, right? And then somehow convert it into this format, right? Just like what we've been doing here, right? Here's the problem though. Does it say x1, x2, x3 or anything like that? No, it just says 0, right? So that just simply means, okay, well, whatever transformation is, that's just times by 0, right? So because of that, the first row is going to be all 0. It sounds really weird, I understand. But, that's a good way to explain this if needed. Think of it this way. The transformation is 0, right? So all the changes you have made is a transformation by 0. If that makes sort of sense, right? So, yeah, okay, I think, well, hopefully that makes sense, right? But nonetheless, yeah, I don't want to get too pinned down here. So, again, the second row is going to be 0 again, right? So 0 times anything 0, so it's just going to be just row 0. Third row 0, 4 0. So that actually makes sense, because if you actually do 0, 0, 0, you guys can see, right? 0, 0, 0, 0, 0, 0 times x1, x2, x3, what are you going to get? You're going to get 0x1 plus 0x2 plus 0x3 gives me 0, and so on and so on, which actually fits your overall W vector, right? So because of that, this is our answer. I'll let you observe that for a while. B, same idea. X vector is 4 by 1. This one is 3 by 1, right? So, oh no, I erased this. Okay, so again, same idea, using x as a reference, x vector as a reference. What was it? So yeah, so it's 4 by 1, so identity matrix is going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? So let's look at it here. 7x1 plus 2x2 minus x3 plus x4, right? So let's focus on one at a time. 7x1, which row has x1 defined? First row, right? x1, x2, x3, x4, right? So 1 times 7, that's going to give me 7. Plus 2x2, x2 is definable here. And that's times 2, so that becomes 2 right there. And negative x3 is defined in the third row, and it's negative, right? So it's minus 1, so minus 1 goes here. Plus x4 is just 1, so it gives you 1. So that completes this line. Let's look at the second one. x2, x3, both plus, right? So it's going to be just 0, 1, 1, 0, right? Because x2, x3. This one is negative x1, right? So x1 is definable in first row, so that times negative 1, negative 1, 0, 0, 0. That is your answer. That is your A, right? So again, not hard. You just have to, get comfortable with the format. Next one is 14C. 14C. I thought I'll do with some even numbers as well, right? But again, same idea, right? So your x vector input is 3-dimensional. Output vector is also 3-dimensional. So we're using x vector as a reference to get and use the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And so this is our net. So let's find out what change. So these are the changes. So let's follow this change transformation instruction to make a new to find the A matrix, right? So x1 plus 2x2 plus 3x, right? Plus x3, right? So x1 right here, no other changes, so I'm just going to put 1. x2 right here, but times by 2, right? So that becomes 2 in the middle, so 2 goes here. x3, just x3, right? Not changes, so that's going to be 1, 2, 1. This one's going to be x1 plus 5x2. So x1, no changes, so just copy 1 here. x2 right here, but times up by 5, so it's going to be 5 here. Nothing, there's no mentioning of x3, so just going to be 0. So it's going to be 1, 5, 0. Here, only thing they mention is x3, right? So I'm just going to put x3 here, 1. There's nothing else mentioned, so it's going to be 0, 0, 1. And that's going to be matrix X. That's pretty, so again, pretty simple. 15. So 15, yeah. Okay, so again, see, I don't know why they ask questions this way. It's pretty obvious, but they're just trying to complicate the problem. We've been doing this for a while, so I don't know why they would ask this way. But nonetheless, so this is the equation this is the linear equations that are given, right? So converted into AX, this format that we all love and adore. So it's going to be A is going to be this one, X vector is going to be this one, and W vector is going to be this one. This should be pretty self-evident, right? Because if you times this with this, it will give me this. And that equals that, right? So really this is, and this format should be very familiar with you, right? So, 3, 5, negative 1, plus 1, negative 1, 4, get the idea, right? So if I times them together, this will give me this. And that, both of this is going to give me your constant column. So again, nothing too difficult. Here it's even more ridiculous because they just ask you, well, tell me what the W vectors are when we give you the X vector. right? So it says t negative 1 to 4, right? So that's just saying this is x1, this is x2, this is x3, right? Like, it's just simple algebra, right? So there are two ways of doing it, substitution or matrix multiplication, right? So if it's substitution, you literally just sub in, right? So x1, so remember, these are all x1, x2, x3, just like here, right? x1, x2, x3, right? So all this are being times by negative 1. So 3 times negative 1, 4 times negative 1, and just follow the suits. Technically it says. Oh yeah, don't worry about the bracket. I just do that so that aesthetically I know which number and where it's being substituted into. Really doesn't matter, right? Just my personal style, right? Too much comp 1631. Remember that last assignment? Oh man, I was overcomplicating the coding recommend guideline or that sheet that Pospisil gave us. Anyway, yeah, okay, I really need to stop talking about my stuff. So anyway, so if you sub it all together, right, that's gonna give you the constant column. So if you sub all this, you're gonna get 3. Sub all this, negative 2, negative 3. So yeah, that's your answer. This is gonna be your W vector. 3, negative 2, negative 3. The matrix multiplication, same idea, right? So you're starting with this, and we're just timesing these, except now we know what x1, x2, x3, right? So just put it, so sub in the x vectors, times it together. So remember the rule, right? So this times this will give me 3. This times this will give me this. And the third row times this will give me this one. So either way works. They ask you to do both. So I guess they want you to know what those two methods are. But ultimately not too difficult, right? So you could say, well, how did the question phrase? 15. Then compute. Oh, okay. They don't even directly say give me the. But ultimately, the W vector is going to be 3, negative 2, negative 3, right? Oh yeah. As for the standard matrix, right? So this thing is the standard matrix. So A is the standard matrix. I use that term, but I did say that matrix A that is being times to the vector. That is the cause of transformation, right? So, okay, the word is out now, right? Official term for that A that causes transformation is called standard matrix. Now, I have talked about this with Maria and also Carlos. It seems like, because, I mean, how we calculate, we base on the identity matrix, right? And then we make a bunch of changes to it. So that almost sounds like elementary matrix, but multiple versions of elementary matrices, right? But that's one way of looking at it, but ultimately that's actually incorrect. Although, if that helps you memorize it better, go for it. But that's not quite the case. It's like saying this. Carlos gave me this great example. Like for example, if I have 3, right? You could say technically it's the multiplication of prime number, right? So for example, let's say 3 is like 1 or 3, right? So you could say prime number is 1. So 3 is really multiplication of a prime, right? But that's not like number-wise that makes sense, but logically that makes no sense, right? 3 is a prime, just like 1 is a prime, right? So I don't think we have to get to that level just yet. My problem is that I have to try to like categorize everything so that I can use those terms like lawyers, right? So, but again, most of you are tuning out now. So, anyways, that's that. We in the next section we are going to finish the rest of them from 21 to 21 to 26. So, I will see you in part.